Welcome back. In the last class, we discussed about HSQC and HMBC, that is coupled HSQC and coupled HMBC, where I took the example of a molecule like this, where we saw in the HSQC spectrum, there are two carbons for this hypothetical molecule which is chosen. At the chemical sheet of carbon A in the carbon dimension, you get a single P. Whereas at the chemical sheet position of carbon B in the carbon dimension, you get a single P. So there is no doubt in this molecule, in the HHQC spectrum, in the carbon dimension, there was a single peak. Because it is a coupled HSQC, we saw that in the direct dimension, that is in the detected dimension, we saw two peaks. It is a doublet. For example, at the chemical sheet of A, we got a doublet because of coupling of this carbon A with this proton A. Similarly, at the chemical sheet of carbon B, in the direct dimension, we saw a doublet. This doublet is due to coupling between carbon B with proton B. And remember, this spectrum is shown, satellite spectrum is shown by enhancing the intensity of the proton spectrum. But in the HSQC spectrum, central peak is not there, that is absent. You only see two peaks, doublets due to carbon proton couplings. This is what we observed and this is what we discussed. On the other hand, when we saw the HMBC spectrum, we observed that carbon A has a long range correlation with proton B, HB. This carbon A has a long range correlation with proton HB. As a consequence, in the carbon 13 dimension, at the chemical sheet of carbon A, you saw a cross peak at the chemical sheet of proton B. In the direct dimension, you see it is chemical sheet of proton B. And cross peak was seen at the proton position of B at the carbon chemical sheet position A in carbon dimension. Similarly, for carbon B, the cross peak was seen at the position of proton A. This is heteronuclear multiple bond correlation, wherein you will see that one bond correlations are efficiently suppressed. You don't see a cross peak arising due to HSQC. They are all suppressed. I hope you understand. This is the major difference between coupled HSQC and coupled HMBC. HSQC gave me the direct correlation between carbon with its attached proton, which is a doublet in the detection dimension due to its coupling with attached proton. Whereas in the carbon dimension, it is a singlet. I am repeating again. So in the HMBC, carbon A gave a correlation to proton B, which is 1 to 3 bonds away. You saw the cross peak. You can see it here in the carbon. For the carbon A, the cross peak is seen at HV. Similarly, for carbon B, cross peak is seen at proton A. Okay, that is so far was good. Now, let us lengthen the molecular fragment. Let us see what happens. See, up to this was known. We understood HSQC and HMBC spectrum for molecule up to this fragment. Now, what we have done is we have extended the molecule, lengthened it by adding a CH group here and adding a CH2 group here. Now, let us look at the proton spectrum. What is the proton spectrum? If I look at the proton A, that is a triplet because of its coupling with two equivalent protons. So HA has to be a triplet. What about HB? HB has to be a doublet because of coupling with this CH proton. Of course, there is a CO here and 2 bonds away, and we assume that long range coupling between this proton and this are all not seen. So we are seeing only coupling between this Hb with this CH proton and this Ha with this CH2 proton. That's all we assume. So as a consequence, this Ha is a triplet and Hb is a doublet. That we all know how to get the multiplicity pattern. We have already understood long back. So this is what it is. But if I take into account the carbon coupling also, in the 1s NMR spectrum, what happens? Carbon A splits into a doublet because of proton A. Remember, carbon A splits into a doublet because of proton A. So at the proton chemical shift site, what is going to happen? You are seeing a doublet. What are these doublets? These are nothing but the satellites. If I look at the proton peak, this Ha peak is having a single peak like this, and because of C12 attached proton, and there are two small peaks on either side, they are called satellites. This we know that, okay? We discussed in the previous HSQC. Exactly, if I take carbon B, that is also a doublet in the proton spectrum which appear as satellites. That's fine. Now we will understand more. We have lengthened the molecule. We have brought in CH2 here and CH group here. Now what is going to happen for the satellite spectrum because of this group? We know we have already analyzed spectrum of satellites long back. I hope you remember. Now each line of this doublet, which are satellites, are further split into triplet because of coupling with two equivalent protons. Remember, when we wanted to analyze the A prime X spectrum, we broke the symmetry and we saw the coupling between protons in the satellite spectrum, which was invisible in the proton spectrum. Exactly similar now, this carbon is having coupling with this proton A and split this into doublet which appear as satellites at the proton chemical shift. That satellite, each component of the doublet will be split into a triplet because of CH2 protons. Okay. Now similarly, carbon at the proton position of B, because of splitting with carbon, it is going to be a doublet, which again appear as satellites. What will happen to the satellites? It has a long range coupling. This proton has a coupling with this proton. So each line of the satellites is going to be a doublet. So now you are bringing in HH coupling between protons in the satellite spectrum. You understand now we are seeing two types of coupling. One is directly bonded carbon proton coupling, and also we are looking at HH coupling in the spectrum. Now let us see how the HSQC spectrum appears in a molecule of this type. So as I said again, carbon base splits into a doublet and appear as satellite. Each doublet further split into a doublet because of CH proton. That I just now discussed. Okay. Now carbon B, as I said, is splits into a doublet because of proton B, and each line of the satellites is split further into a doublet because of its coupling with CH proton. That's what we know from the 1D spectrum. Now let us look at the HSQC spectrum. Now we have taken the elongated molecule where the CH group is added here and CH2 group is added here. How does the coupled HSQC spectrum look? Before adding these two groups, there was no central peak and we were seeing only two peaks here. Remember in the previous HSQC spectrum, we saw only two peaks because of coupling of A, carbon A with proton A. The satellite which you see in the proton spectrum was seen here in the proton dimension. In the carbon 13 dimension, we saw a single peak that we analyzed. Now, because of coupling of this carbon, this proton with this proton is a triplet. That's what you are seeing in the proton spectrum. This Ha is a triplet because of its coupling with CH2 protons. Now, this coupling is going to be reflected in the proton spectrum. You know that. When you analyze the satellite spectrum, in the satellite analysis, I showed you the homonuclear couplings are reflected in the satellite spectrum. This triplet with the HH coupling is seen in the satellites. So each component of this doublet is further split into triplets because of HH coupling. Understand? In the original HSQC spectrum, you had only two peaks because of coupling of carbon with proton. Now each line of this is split into a triplet because of coupling with two protons. Hence, it is going to be doublet of triplets. In the direct dimension, it appears as doublet of triplets. Whereas in the carbon 13 dimension, it is still a single peak. Is it clear? There is no change at all. Now, how does the carbon B coupling with proton and carbon coupling with this CH proton appear? Of course, this in the proton spectrum, at the site of chemical shift of proton B, this carbon splits this into a doublet. So we saw again two peaks will be there. In the previous HSQC we saw it is a doublet. But now each component of the doublet is split into additional doublet because of coupling with this proton. So it appears like this. Exactly that's what we are seeing. In the coupled HSQC, now we have brought in proton-proton couplings also. But in the carbon 13 dimension, it is still a single peak. Is it clear? Now, in the coupled HSQC, without proton-proton couplings, we saw only a doublet. When the proton-proton couplings are introduced, they appear in the satellite spectrum, which are reflected in this HSQC spectrum. That's what I wanted to say. Okay. Now this one, interestingly, this spectrum, center of this to this center is going to give me coupling between carbon to proton, this carbon to this proton, direct one bond coupling. Okay. Now, if I take the separation between this and this, what do I get? We get coupling between this proton and the CH2 protons. That's what we are going to see. And again, in this case, this separation gives me coupling between carbon and proton, Cb and Hb, and this separation gives me coupling between this proton and this proton. So this is the analysis. Analysis become very simple now. Same thing now, let us look at HMBC. This was HSQC. Now we are look at HMBC. What did we say in the HMBC spectrum without bringing this into account? At the site of carbon B, we saw a peak because of long range coupling with this proton. At the site of chemical shift of carbon A, we saw a cross peak because of its correlation with this proton, long range coupling. Exactly same. So, at the site of carbon A, we must see a correlation with proton B. No doubt. We see at the site of A, we see the correlation due to proton B. Now, this proton B is split into a doublet because of this proton. So, each line of this satellite should be a doublet. Very clearly we are seeing that. Each line of this is going to be a doublet. Are you all with me? I hope You're all with me. First, now Ca is going to give a cross peak with at the position of Hb. But this is a doublet because of this. So each line of this will be a doublet. This is what we are seeing. Now look at the carbon B. What is happening to carbon B? It is going to give a cross peak with proton Ha. That's what we are looking at the old HSVC only. And now come to the extension part now. Now carbon B gave a correlation peak at proton A. What is happening to proton A at the site of carbon A? It is split into a triplet because of these H2 protons. As a consequence, what is going to happen? Each line of this doublet is split into a triplet. That's what is happening here. Additional splitting because of the long range coupling. In addition to seeing this CB correlation to HA, you are also seeing this HH coupling here. Very clear. Okay? You are all with me. What is that? Simply look at this one I have written. This splitting is going to give me 3JCBHA, 3 bond CBHA. I'm sorry, this one, 3B CBHA, 3 bond. That coupling is there. Plus, the doublet is split because of 3J HACH2. Not 3J, it is 2J, I think. HACH2. It is 2 bond. 2 bond HACH2. That's what you are going to see. Exactly here. Now look at Ca. This is going to be Ca-Hb coupling plus you are having coupling between Hb and the CH. So fantastic, long range couplings of the protons are also reflected here. So this is because of the additional groups here, addition of these groups, coupling between this and this is reflected, coupling between this and this is also reflected here. So this is what happens if you bring in proton-proton couplings also in the HMBC spectrum and HSQC spectrum. I hope you understood. Now we have dealt with 4 cases. In a small molecule, without these additional extra groups, we only saw this fragment. In the coupled HSQC, we are going to see a doublet at the site of this because of this coupling, doublet at the site of this carbon because of this doublet, this proton in the direct dimension. And the carbon 13 dimension gave me chemical sheet of each of them. In the HMBC, at the site of carbon A, we got the correlation to proton B. Okay. And at the site of carbon B, we correlation to proton A. Now in the next 2 example, we lengthen the molecule with this and this. Now exactly same we saw in HSQC. In addition to that, in the satellite spectrum, coupling between this proton and this proton is seen at Ca site in HSQC. Coupling between this proton and this proton is seen at the site of Cb in HSQC. On the other hand, in the HMBC, this carbon correlates to this proton and this coupling is seen. This carbon correlates to this proton and this coupling is also seen. So we took 4 examples, 2 examples without bringing in HH couplings in the satellite spectrum. In the remaining 2 examples of HSQC and HMBC, we also introduced proton-proton couplings. I hope it is all clear for you. Okay. This is what it is. Now let us take the simple example of ethyl acetate and try to analyze the spectrum. Now, this is a 1H coupled HSQC. This is similar to the molecule which was seen before, where we will see HH couplings and CH coupling everything. Now, what is the first one? We know, we are confident this must be CH3, which is high field, which is coupled to CH2. Okay. In the proton spectrum, this is CH3 and it is a triplet because of CH2. That is clear. And this is CH2, it is a quartet because of CH3. That is clear. Now, in the HSQC spectrum, what will happen? This carbon is going to correlate with these three protons. Exactly. You get a doublet because of one bond CH coupling. Understand? But now each lane of this doublet is a triplet, one-to-one triplet, because of coupling with CH2 protons. That's what we observed in the previous example. So in a realistic example, you are able to see that. But in the carbon 13 range, carbon 13 dimension, you see only one peak, and that is the chemical sheet of this carbon. All information you can get in one simple experiment. Let us look at this one. What is this one? This is CH2. In the HSQC, you see a doublet because of correlation of this carbon with this proton, and it is a doublet because of 1JCH, and each lane of this doublet is a quartet because of coupling with these three protons. Very clear? There is no doubt at all. Everything is very clear, right? Now CH3CO, if you look at this, what do you expect? For this CH3CO, this in the proton spectrum, it is a singlet. Okay? And these two are carbon 13 satellites. And there is no long range couplings of proton for this. They are all far away. So it remains a doublet in the HSQC spectrum. No other proton-proton couplings are seen. I hope you are all with me. Okay? Now, the same thing if you look at the HMBC, what happens? Interesting thing. Exactly. At the site of CH3, you must see correlation to CH2 protons, long range coupling, long range correlation. That's what we see. Exactly. CH3, at the site of the CH3, you are seeing correlation to CH2 protons. But because of this coupling to this, what you should expect? You should expect each lane of this doublet into a quartet coupling. You know, CH2 is coupled to three protons. That multiplicity is seen here. See? CH3 proton correlates with CH2 proton, and here CH3 proton correlates with CH3 proton. And here CH2 proton has a long range correlation to CO carbon also. HMBC is the biggest advantage. You can get correlation to remotely bonded proton with carbon. If this carbon is there, its remote bonding with this proton can be seen. Remote bonding of this carbon to this proton, if possible, we can see. So it is only 2-bond, 3-bond correlations can be seen. That is the example I gave for HMBC. We took the real example of ethyl acetate and we analyzed the spectrum. I suppose you all got the point how to analyze the coupled HSQC and coupled HMBC spectrum. Remember, this is this one which you routinely use in your carbon 13 NMR, in your proton NMR. If you want to study synthesis of molecule and get proton carbon correlation, proton carbon chemical sheets, couplings, and how to assign each carbon and carbon chain, you can get the proton nearest neighbor by COSY, TOXY, etc. But if you want to find out which carbon is next to this proton, so you can do this type of experiment, long range correlation to proton carbon like HMBC type experiment. Okay, so this is what it is. Now next thing I wanted to say is, in the same HSQC, HMBC, HMQC spectra, we can bring in carbon 13 decoupling. So far, remember, we saw carbon coupled HSQC, carbon coupled HMBC. Now, we can also do heteronuclear decoupling. Remember, in the proton spectrum, in the carbon spectrum, we can completely decouple proton. And what we are going to see, for each carbon, a single peak. In the proton spectrum, you are going to see carbon 13 satellites. That's what we saw in HSQC. What we can do even the carbon decoupling. In addition, while detecting proton, you can do carbon decoupling. Then what will happen? The satellites will disappear, merge into a single peak. So what you will expect in the HSQC spectrum? The two doublet you saw are satellites now merge and give a single peak at the center. Where you see only a single proton peak, you are going to see a correlation peak. That's all. Only thing is splitting is removed. The coupling is removed. No more splitting. You will get correlation at the respective chemical shifts. Coupling information is absent. You don't see additional splittings in the HSQC spectrum. Look at it. Now take a molecule 3-heptanon. 3-heptanon molecule, we have how many carbons? 1, 2, 3, 4, 5, 6 different carbons. Of course, the CO carbon will not appear in the HSQC or HMBC spectrum because it is not attached to protons. Now, this is a decoupled, carbon 13 decoupled. That means when you are observing proton, you are decoupling carbon 13. So, let us take this example of proton 7. This is a CH3 proton. In reality, in HSQC, in a coupled HSQC, this was a doublet, right? But now, because you are removing the carbon proton coupling, you are seeing only one peak at the center. Very clear, right? This is a coupled HSQC. You directly get the correct at this. Now, what you do is go along this axis, you get the carbon chemical sheet. Go along this axis, you get proton chemical shifts. It directly gives you carbon proton chemical shifts in corresponding carbon and proton dimension. That's all. No coupling information. Now look at the proton 1. Go here, you get proton coupling. Go here, you get carbon coupling. So all these things we can easily be obtained. So coupled carbon HSQC and decoupled HSQC, the only difference is multiplicity is reduced, and in the decoupled HSQC, only correlation of chemical shifts of heteronuclear space directly coupled carbon proton or carbon nitrogen, such information only you can get, nothing else. Okay, so as I said, HH couplings are removed, and this is how you get the correlation. Now the same thing if you do the HMBC, what happens? At the site of this proton, CH3, you have a correlation, this correlation is seen at CH2 carbon. For example, CH2 carbon can give correlation to this proton or this proton. Okay, look at this one, proton 6. Okay, we will start with one of the simple one which we very well know. Okay, here itself, carbon 1, this one. The carbon 1, you see, it is go along this axis, you get a carbon chemical shift. You can see the correlation for this is seen at here, H2. See, this carbon 1 is correlated to this proton 2. As you can see the peak here. This carbon 1 is giving a correlation to proton 2. Then you may understand, you may say, what are these things coming? That is HSQC correlations which are not completely suppressed here. In this experiment, in fact, in the real experiment, you have to suppress these things, but it is not suppressed. That's why it is marked in squares here. This is because of HSQC correlation, you ignore. Those who is marked in squares, you don't worry. Now you will see carbon 1, there is a strong correlation to proton 2. Now carbon 2, if you see, take, where is carbon 2? Here. Carbon dimension, okay, this one. So this has a strong correlation to carbon, this carbon 2 should have a strong correlation to proton 1. So this one, where is this proton 1? Somewhere here, C1 should be there. It is all hidden here. Huh? Okay, somewhere there you must see. Okay, it is or you can see carbon 2 is here, I'm sorry. Carbon 2 is here. Okay, okay. Carbon 2, you see, there is a strong correlation to proton 1. Now, I'm sorry, I was not seeing this properly. See, carbon 2 is here. I was looking elsewhere. Now, it has a strong correlation to proton 1. These are the long range correlations. Okay, now look at C4, carbon 4. It has a correlation to 5. Long range correlation, it can correlate only to this proton. So, like this, HMBC spectrum gives you coupling to 2 bonds or 3 bonds away protons. The correlation to protons which are 2 bonds or 3 bonds away. Again, it is a decoupled HSQC. Okay. So now, what is this? Okay. Now we'll go to the next topic. I think you are all familiar with the HSQC, HMBC, HSQC talks. Is couple of 2D experiments I introduced. Now I will introduce one more thing which is called homonuclear and heteronuclear J result. They were all correlation type 2D experiments. Now we will see resolve type experiment, both homonuclear and heteronuclear. See, in this case, it is simple like a spin echo sequence. How the spin vectors behave, we understood this by vector diagram long back. This is a pulse sequence. You have a 90-degree pulse, and then we have a time delay T1 by 2. At the mid of the T1 period, you apply a 180 pulse, and then after the T1 period, you start collecting the signal. So this is a simple homonuclear 2D J result spectrum. In this case, idea is what it does it puts chemical shift information in, along one axis and coupling information in the other axis. In the real spectrum, what happens is in this dimension, not only you get chemical shift, you also have the coupling information. It's because in the direct dimension, both is there. Coupling with chemical shift and carbon both are there. Because in the detection dimension, you are not doing anything. You are simply collecting the regular spectrum. So all coupling and chemical shift informations are present. Whereas in this direction, you have only coupling information. That's all. In the J result experiment, simply a two-pulse sequence like this, 90 T1 by 2, 180 T1 by 2, that is the sequence. And then all you have to do is, when you do an experiment, this is an example for a A3X2 type, CH3 coupled to CH3, CH2 coupled to CH3 or CH3CH2 group of ethyl alcohol. Now, because of the J coupling, it appears it is as if it is tilted by 45 degree here. So this has because delta and J both are present. So now what we can do is this one, because both are present, I can tilt the entire spectrum by 45 degrees like this. This is called 45-degree projection. Now what are you going to see? This is the chemical sheet of CH2, this is the chemical sheet of CH3. And what you are going to get in this direction? In this dimension, you get this separation gives you JHH. This is JHH, this is JHH, this is JHH. So multiplied lie along the F1 dimension, that is indirect dimension, whereas the chemical shift now along direct dimension, that is T2 dimension. Look at it. So what is the advantage of it? You have resolved both the information, chemical shifts and couplings are separated out in 2 dimensions. Remember, this is called a J result experiment. In the J result experiment, it is simply a two-pulse sequence, 90 T1 by 2, 180 T1 by 2, and you start collecting the signal like a spin-echo sequence. We observed this, we understood how the spin vectors behave for CH vector, CH2 vector, and CH3 vectors when we were trying to understand APT. Remember, we understood spin echoes. Exactly. So in this real spectrum, actually there is a tilt. And if you take the 45-degree projection of that, now you get only chemical shift along this direction. In the T2 dimension, you get only chemical shift. In T1 dimension, you get only J couplings, nothing else. So you have separated this information. Now I'll give you an example like this. I have a complex spectrum. I have a complex spectrum like this. Now, this is a multiplicity pattern. I do not know which is triplet, which is quadruplet, which is doublet. How do I do that? If I have to analyze this complexity, it is a difficult job. As I said, why can't we now separate out the information of chemical shift and J couplings into different dimensions? Let us try that. What I will do is I am doing the coloring. Now I know this and this is a doublet, this and this is a triplet, like that, this and this is a doublet. Because I know this, I am coloring. How did I know that? I took the J result spectrum and tilted by 45 degrees. So this axis gave me J coupling and this axis gave me chemical shifts. But exactly at the chemical center of this you get chemical shift. Then I know if I take 45-degree tilt, this and this are coupled. If I take 45-degree tilt, I know this and this are coupled. So like this, we can make the assignment of all the multipliers in a complex spectrum by taking J resolved spectrum. So you are separating out the information of J coupling and chemical shift in two different dimensions. This is what it is. You know, one interesting thing you must see, when I take the tilted spectrum, 45-degree tilted, you are getting only chemical shift here. What does it mean? See, in the normal spectrum, it would have been a doublet and this would have been a triplet. So now what did you do? In fact, if you take the 45-degree tilted J resolved spectrum, it is as good as telling in this dimension you have done the broadband proton decoupling. It is analogous to decoupling of one proton coupled to all the other protons. All the coupled partners of you are completely removing their couplings. So what are you going to see? Only singlet peaks. Is it similar to carbon 13 with the broadband decoupling where you got only single peaks for each carbon? Exactly analogous to that. So if you take the 45-degree projection, each peak in the J resolved spectrum pertains to a single proton. It is like telling this is a spectrum with broadband proton decoupling. Or in other words, it is a proton decoupled proton spectrum, broadband proton decoupled proton spectrum. Similar to broadband proton decoupled carbon spectrum, it is a broadband proton decoupled proton spectrum is what you are going to see when you take 45-degree tilt. See, this is the advantage. Okay, fantastic spectrum now. It is a broad, I have removed the couplings. I am showing you this is like a completely decoupled spectrum. This is one chemical shift, all the 6 chemical shift, and in this dimension you are getting the J couplings.